Suppose I should my mic. Hey, what's up? We're live. We are live, both on TikTok and YouTube. Excellent. This mic's for TikTok. This mic's for YouTube. Sorry if it was loud. I guess there's not really anybody here yet, so it doesn't matter. It's been a while since I've been live. Let's do like that, maybe. How's the sound quality? Sound okay? How we doing? Somebody say hi to me. What should we talk about? Okay, good. Glad it sounds good on YouTube. How's TikTok sound?
Sorry. Your annual. Our niece is being broadcast to the world.
I guess that's fair. Hello.
Also, ow. Sorry, I'm killing myself. I think there's mail and stuff down there. Just make sure you don't.
I don't think any of that's visible. I think we're okay. I don't know if it's maybe visible from TikTok. Hello, welcome. What's up? How's everybody doing? Yeah, maybe I will fix that. Hang on a sec. Oh, no, I think that's fine. Okay, we're good. Hello, hello. Let's talk about the brain. What do we want to talk about? Let's see, I've made quite a few videos. I haven't been live recently. It's been a couple weeks. I haven't been making videos the last few days either. Harm and I finally got moved into the new house as of the 1st, and it has been bananas. It has been wild. This new house is pretty nice, but it still has just an absurd amount of work that needs to be done to it. And yeah, like for instance, we don't have a kitchen. That's super fun. We're working on it. Harm and I will probably work on it more tonight. Hopefully we'll have cabinets within the next few days, and then we got to get a sink, put in all the appliances, and we'll be ready to go. So in the meantime, yeah, I haven't really had the time to make videos. I've just been super busy with this house, and I haven't had the time to go live, or I would be. Anyway, I missed everybody here. I'm sure you all miss me too whenever you show up. Speaking of which, I should probably invite some people. I don't know. But yeah. Let's see. I just released a video. What was that about? I released a couple videos today. One was, huh?
Glutamine.
Oh, glutamate. Yeah, as a neurotransmitter. I don't know. I guess I'll talk about that for a bit. So glutamate's really cool. It's one of the main neurotransmitters that we learn about in school. And it's one of my favorites. I love all the neurotransmitters because they all do wild, crazy stuff. Glutamate is really cool because it's the primary excitatory neurotransmitter in your nervous system, which means that it's required to make things happen. Glutamate basically, wherever it functions, makes the next target cell more likely to fire, whatever that is. Usually another neuron. I think glutamate receptors, I might be wrong on this, don't quote me on this, but I think glutamate receptors make up about 80% of your receptors. That's how widespread they are. It may not be that many, but I know it's pretty high. Neurotransmitters are cool. I know very little about them, though. Yeah, it is bananas. Well, you're in the right place because you'll learn about them here. I think my next video will be on gamma aminobutyric acid, which is GABA. A lot of people have heard the word GABA, but don't really know what it is. GABA is the primary inhibitory neurotransmitter, as well as there's another inhibitory neurotransmitter that's pretty widespread called glycine. So I think I'll probably do a video on that one as well. But talking about glutamate, the thing that's really cool about glutamate is it's required for long-term memory, what we call long-term potentiation.
Click on the light. On the battery.
Sorry, 1 second.
Sorry, you just listened.
That's okay. Is that not good?
Fine.
I don't know. Okay. Not to get derailed. Sorry about that. But hopefully you can see me a little bit better. Anyway, let's see. Glutamate. Glutamate is required for long-term potentiation. LTP is what we call it. What that is it is the cellular mechanism for Donald Hebb's rule, which is neurons that fire together, wire together. So basically, that's a colloquialization of what Hebb's rule actually is, or what he said. But it basically gets the point across. When you have two sets of neurons firing at the same time, they start to grow synapses out towards each other, and they become connected. And so they grow towards each other, they become connected. And the more you use them together, the more those connections build and strengthen. And that leads to two things. One is that makes that synapse more efficient, right, for the next time. And the second thing is that every time you fire one set, the other set will fire as well, because they're intimately connected now, right? And this is how we learn to pair two things together. For instance, being thirsty and knowing you need to reach for water when you're thirsty, right? Those ideas are not immediately paired together. They become paired together because drinking water. Hi, Pekka. How are you? Drinking water greatly reduces the amount of, I guess, discomfort that you feel when you're thirsty. So that's rewarding. You'll learn that. Pekka, we're just talking about glutamate. I just released a video for that. Yes, thank you. Yeah, I was just saying I haven't been live in like probably about 2 weeks because we just moved into the new house and it is still in shambles. We're working really hard, tirelessly. Okay, well, I hope you have a good shower. Yeah, we're working tirelessly to get this house livable. And so I haven't been able to go live. I haven't made a lot of videos, but hopefully I'll be able to like get back on that. I'm just talking about glutamate now. But yeah, so glutamate is part of this process of long-term potentiation where we are taking two ideas and we're sticking them together, right? And those ideas could be anything. It could be like, every time I drink coffee, I think about my mom, right? It could be literally two ideas that you're sticking together. It could be a motor function, right? Every time I'm thirsty, I reach for water. Whatever the case is, you're sticking these multiple things together via these synapses as they're created. But how do we create those synapses? We do it through glutamate signal. So glutamate is a primary excitatory neurotransmitter of the central nervous system, right? And basically all that means is that it acts on receptors to make it more likely for the neuron that it's communicating with to fire. So you have one neuron releasing glutamate, the other neuron is receiving it, and as it receives it, it becomes excitable, it depolarizes and fires an action potential. But the way it's doing that is through two sets of receptors. Those receptors are AMPA, and NMDA receptors. The thing about AMPA and NMDA is they have surprisingly different functions, right? So AMPA functions like a regular receptor. It receives the neurotransmitter and it gets excited and it tells the cell to be excited. It gets an excitatory postsynaptic potential is what we call it. And it slightly depolarizes that cell, makes it more likely to fire. But then you have NMDA receptors, right? And they also act on glutamate. The problem is that they actually have a magnesium block, which means that even though they might be receiving glutamate, they still can't allow calcium to come into the cell. That's what they are. They're a calcium channel, right? So in order to allow calcium to come into the cell, you have to remove that magnesium block first. This is what we call coincidence detection, right? We don't want this process to happen unless we have fulfilled something. And the thing that we need to fulfill actually has to do with the strength of the synapse, the strength of the signal, And it also has to do with the timing. You have to time it correctly. So when you just need a process to happen, you just want to excite something, make the process happen. You don't need the NMDA receptor. You just need your AMPA receptors, right? AMPA is just receive the message, and send it through. That's it. Thank you for the message. Okay, it's out of here, right? That's it. And that's easy, simple. But when you receive a really strong message, you are electrically stimulating this neuron. And while it's electrically stimulated at the correct voltage, that magnesium block is removed, right? And when you remove that magnesium block, now we can receive glutamate. So this is why it's called a coincidence detector, right? What a coincidence. I have both glutamate and I'm stimulated to the correct voltage. So once I'm at the correct millivoltage and I have the correct glutamate, now I can influx the calcium. And that influx in calcium creates a cascade event inside of the cell, which is a fancy way of saying it just sets a lot of stuff off. It sends a wave, right? And that wave goes to the internal mechanisms of the cell into the soma, which is the cell body. And what that ends up happening is causing that cell to produce tons more AMPA receptors. So now we're going to produce a bunch of AMPA receptors, and we're going to send those back out to the membrane, right? And as we're sending these more AMPA receptors out into the membrane, that membrane is actually getting bigger. So now we are taking a dendritic spine and we are growing it, right? And at the same time, the synaptic terminal that's talking to us, the one that's sending the glutamate, is going to wrap around us. So we're basically what we get is a lot more surface area, right? And that's great. That's exactly what we want for a long-term connection. So again, this does two things, right? One, it makes the connection more efficient, right? Because now our presynaptic neuron can send even more glutamate, and our postsynaptic neuron can receive that glutamate because now we have more receptors. It's bigger, more surface area, lots more efficient. Give me more, right? But the other thing that we have is that it's more stable. It's a larger structure, and so the structure will last a long time. And by creating structures that are like this, that are more stable, they last a long time, they're more efficient. Hey. Oh, cool. Resist oppression. It's good to see you. Feel free to ask questions when you tune in. And yeah, it's just good to see you. Glad you're here. Anyway, that's why this mechanism is used for long-term potentiation, right? Because this is the actual physical mechanism of building a memory. When you have a memory of, say, a dog, right? Generically, you might picture a dog as an amorphous creature because dogs can have long noses, they can have short noses, they can have big ears or short ears, or ears that stand up or ears that flop down. They can have little legs and long legs. They can have long bodies with little legs like a dachshund, whatever. Dogs can come in all sorts of shapes, right? And sizes and smells, and they, different fur textures. And so all these different aspects about them can be different. If I tell you, think of a dog, you probably don't think of one dog. Usually people don't. Usually people think of what's called a dog prototype, right? A prototype. And it's sort of an amorphous amalgamation of different things that are dog-like in quality. But it's not usually a solid animal. That's different if I say, think of your dog, right? When I tell you, think of your dog, you're more likely to think of a very solid image. And that's your actual dog. When I think of your dog, you know what your dog sounds like when it barks. You know what your dog smells like. You know what their fur feels like. You know what your relationship to them is. You know what their name is. You know various facts about them, when they were born, when they might have been injured, or at this time you took them to the vet, whatever. You have all this information about your dog, right? But how do you get this information and retain it, right? And the way we retain it is through this long-term potentiation mechanism. I can recall facts about my dog because I have stable connections neurologically. What does that mean? It means that I'm physically connecting the neurons together through this glutamate action, where I'm activating these NMDA receptors, and they're pumping AMP a receptors out into the cell membrane and physically making this connection bigger and stronger, right? So glutamate's very important. Glutamate not only stimulates neurons, but it also is a very important key player in the formation of new memories, long-term potentiation. And the inverse of that would be long-term depression, which doesn't necessarily take cellular action. It can and it does, but it doesn't always. Long-term depression is the exact opposite of long-term potentiation, right? This is where we are long-term snapping things apart. And the reason we do this is because it's not always important to remember things, right? And you'll know what's important to remember because your brain tends to hang on to stuff that's important. Not always, it can miss things. There are ways to trick your brain. For instance, one of the most common tricks that most people have experienced, and maybe you haven't thought about it this way, maybe you have, but you forget someone's name immediately as they tell it to you. Someone will tell you, "Hey, my name's Todd." And you're like, "Hey, Todd, what do you do for work?" And Todd tells you what they do for work. They're a programmer, da 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 da. And by now, while they're telling you that they're a programmer, you've already forgot their name is Todd. And it's a really embarrassing thing, right? We've all done it. It's just a thing that happens. But the reason it happened is because we don't go, "Oh, your name's Todd. Let me think about that for a second," because that would be weird, right? It breaks the flow of the conversation. It feels odd. But if you did that, you would be more likely to remember Todd's name. But because we don't do that, because it breaks the flow of conversation, it's awkward, we don't always remember Todd's name right away. And because Todd immediately went into our follow-up question, which is, "What do you do for work?" It's a very common thing. Or like whatever other follow-up question, we start absorbing that information instead of their name. So we immediately forget their name, right? There are different ways to trick your brain. Give me 1 second. Drink some water. The process of long-term depression also has a lot to do with expectation and reward. I did a video not too long ago about dopamine and dopamine's role in motivation, right, and reward processing. The thing is that a lot of people make a mistake with dopamine because it's colloquially referred to as the pleasure chemical. But that's not what it is. Dopamine isn't about pleasure. Dopamine is about motivation, and it's not always pleasurable. We know that people can experience pleasure without dopamine, but we also know that people can experience a boost in dopamine and not feel pleasurable about it. This often occurs with expectation. In fact, that's how dopamine fires. It doesn't fire in response to a reward so much as it fires to the expectation of a reward coming. And when that reward doesn't show up, then you see a sort of deactivation of the circuit. And so we unlearn that circuit. We stop pairing it together. We actually physically break the synapse. Dopamine is more for motivation, right? So what that means is that if something is highly motivating, fire a lot of dopamine expecting a reward. And sometimes you won't get that reward. And then generally you should forget that connection. But that isn't always the case. Sometimes chemicals can be really addicting. Sometimes it's not always a chemical. Sometimes it's a process. It could be blinky lights. Could be love. Love can be really addicting. Could be gambling. Could be really anything, I guess. But there is a thing that can happen where we have really powerful dopaminergic reward circuitry paired with something that's actually very unpleasurable, right? But it's because it's deeply ingrained in the circuitry that is necessary for survival. We want to survive, right? For instance, if I'm hungry, I find food rewarding. If I am thirsty, I find water rewarding, right? If I'm lonely, I find companionship rewarding. And so the reason for these reward circuits is to bring us into homeostasis so that we have the things that we need, right? This is for survival. It's a great thing. But like all mechanisms, you can mess with it and it doesn't always work great. And that's the case with addiction. Something happens where this circuitry is hijacked, and so then when the stimulus is no longer rewarding, say the drug is no longer rewarding, rather than disconnecting that association, for some reason your brain says, oh, I just need more of it to get the same reward. I need more of it, and quicker and quicker. And it kind of enters this sort of feedback cycle. You see a few of these with the brain. I actually was just talking about this in another video where, it's kind of easy to just put so I did another video on panic attacks, right? And how, let's see, what did I talk about? So I talked about panic attacks and how they're actually the brain's airway, alarm system going haywire. And this is also due to a feedback loop that happens by mistake. Sometimes this happens when you trick the brain. So I'll that maybe. So here's the thing. Your brain has circuitry in it called the limbic system, which is vital for things regarding survival. And one of the things that it does is it sets off alarms, right? And one of the specific alarms that it'll set off is an increase in CO2. Your brain can't really monitor oxygen. It doesn't have a good way to do that, but it can monitor CO2. And when CO2 levels increase, that is a key indicator that you're not getting enough oxygen, which means that you're suffocating. And this is such a powerful alarm system that this was developed a long time ago. We evolved this alarm system way back before humans even existed, right? Some primal creature had this a long time ago. So, of course, we didn't evolve reasoning until way later, right? My point is, so you have this thing that evolved to tell you when you're not getting enough air. And the reason you have this is because there are very real dangers out in the real world that our ancestors faced, and that we still face today. For instance, you could be drowning. You could be getting crushed by something. Maybe you're stuck in a tight, small space and you're not getting enough air. And so your CO2 is building up, right? You might be breathing in smoke. You might be breathing in gas, like a natural gas in a cave, and you don't realize it. So all these different things can happen and have happened to our ancestors, right? And have killed a lot of our ancestors. But some of us evolved, to have this trait where when we see CO2 spike up, we freak out, right? We're suffocating, and our immediate impulse is to just get the heck out of there, right? Natural mechanism, very important mechanism, obviously. But the problem is that so now we notice that people have panic attacks, and people have had panic attacks for a long time. Sometimes it's been referred to as different things, could be like hysteria or other things like that throughout the ages. But people on occasion have panic disorders. I have one, right? And mine's probably related to PTSD or something else. But most of the time when people have a panic attack, it's not the same as an anxiety attack. A lot of people get them confused. An anxiety attack has a very clear cause most of the time. It's like, oh, I'm overthinking about the future or the past, one or the other. I could be thinking about a relationship. I could be thinking about my job. I could be thinking about driving or whatever triggers me. And this thing can send me into an anxiety attack, right? But panic attacks generally feel like they come out of nowhere, and they actually literally feel like you're going to die. And your symptoms look a lot like you're having a heart attack. And so oftentimes, yes, panic attacks are horrendous. Oftentimes you end up in the ER because of it, right? So there's a huge difference between panic attacks and anxiety attacks. The main one being that you usually can identify a cause with your anxiety attack. And they're generally more manageable too. Panic attacks are much more visceral, and it's because they're working off of this old alarm system that actually has to do with suffocation. We didn't figure that out until much later, in fact, more recently. So I'm going to tell you about that now. Let me get a drink of water. So here's the thing. We developed this And when I say we developed this, I mean like it's been here for such a long time that it is ingrained in our brainstem. And remember what I say about the brain, right? I'm gonna grab my brain. Here's my brain. She's beautiful. Crack her in half. Here we go. So the most inner part of the brain is what has evolved first, right? And so it's whatever is required for absolutely required for survival. I'm saying this is your brain stem right here. Everything in here, the pons, the medulla, all that has to do with your heartbeat, your breathing, your swallowing, your anything that is absolutely vital to survival runs through your brainstem, right? And then as you work your way out, you get things like balance and coordination. You get things like memory and mood regulation and different like excitability and control, sleep wake cycles and things like that. So these things are still pretty important for survival, but they're not immediately necessary, but do become necessary. And then as you go further outward, you have the cortices, which are responsible for your higher cognition. How do I process what the senses are telling me? How do I make relevant use of that information? Yada yada. How do I inhibit myself in whatever way I might need to, etc. So this mechanism that detects whether you're suffocating is deep within the brainstem, right? Because it determines how you're going to breathe. So here's the problem. What do you do if you're suffocating? What do you do? Well, your brain says, time to breathe, right? I need more air. That's basically it. Your brain goes, hey, get the hell out of here and start breathing really fast and really deep because you are not getting enough oxygen. And the problem is that people who are having panic attacks do breathe fast and deep, and it doesn't seem to do any good, right? Actually, it makes the problem a lot worse. Why is that happening? And it turns out that this mechanism that's part of the limbic system deep inside of your brainstem is it's not so much that it detects if there's too much CO2, it actually detects if there's the wrong amount of CO2. And the problem with that is that, so normally this is a great system, right? If there's the wrong amount of CO2, that means I'm suffocating, get the hell out of there, breathe more, and I should be okay. And any time in human history, that has generally been the case, right? Whether I'm in a cave that's full of noxious gas, or I'm breathing in too much smoke near the campfire, or whatever could be causing it, breathing more and getting away from it, the source, will fix that problem, right? So we've evolved for that. What we haven't necessarily evolved for is getting not enough CO2. And the reason why is because CO2 is important for the body, but our body produces it itself as a byproduct, right? And it can build up and become toxic quite quickly. So we actually don't get it from our external environment at all. We certainly don't need it from our external environment at all. And what that means is that we haven't evolved to watch out for our external environment having not enough CO2, right? That is a very weird thing. We never would need that because our body produces enough CO2 for us on its own. So because we have this part of our brain that just says, big brain energy. Yes, correct. Yeah, breathe more. So here's the problem. Yeah, exactly. So problem, resist oppression. So the problem is I have this mechanism that tells me that I'm suffocating when actually I'm not, because my CO2 is off. But the problem is that my CO2 is off in the wrong direction. I actually don't have enough CO2. And in reality, that's not actually a problem. Like really, I don't need very much CO2. I definitely don't need it from my environment. So if I don't have any CO2, like if I literally have zero CO2, that will hurt me. But I need so little CO2 in my system that it doesn't really matter if I'm not getting enough, right? But the brain doesn't know that. The brain interprets it the exact same way. All it knows is, hey, your CO2 is off, right? So it interprets not having CO2 as the same as having too much CO2. And so what does it tell you? It says, hey, you're suffocating, breathe more. The problem is that when we breathe out, we release CO2. The fact that your CO2 is too low is because you're breathing too much. You're actually breathing out too quickly. And what does that do? Well, it tells you that you're suffocating. You start getting what's called air hunger, right? And you become hungry for air. Do we really need CO2? Yes, we do, actually. We do need a little bit of CO2. The case study with the girl with no fear. Oh, yeah, for sure. Yeah, exactly. Resist OP is the resist oppression is talking about when I did this video about, and I had talked about in another live, I think, this woman who couldn't experience fear because she had damaged amygdala. She had a genetic disorder that caused her amygdala to become calcified, and they were damaged and they deteriorated, right? And she's how we figured out that your amygdala are responsible for fear processing in the external environment. But we did learn that she could experience fear when you increased the amount of CO2 she was breathing. She had an immediate and profound panic attack, likely even worse than the average individual. As someone argued in my comments section on YouTube, she probably had an even worse response because she lived her whole life without building any sort of coping mechanism, right? Which is terrifying. So yeah, your brain can't tell the difference between too much CO2 or too little CO2. So when you're getting too little CO2, which can happen when you're breathing too quickly, your brain tells you you're not getting enough air. So what do? You get more air. So you're breathing in fresh air and you're blowing out CO2. And so you're getting rid of too much of your CO2 and getting too much oxygen. But your brain doesn't know that. Your brain, because you're still offloading all this CO2, thinks that you're suffocating. It thinks you have too much CO2. So it sends an even more powerful signal saying, breathe harder. So now we have this horrible, dangerous feedback cycle where the more you breathe, the louder that alarm gets. And the louder that alarm gets, the more you breathe, right? And so as impossible as this feels, really the answer to get out of a panic attack, even though everything inside of you is viscerally screaming to breathe more, you have to stop breathing so much. In fact, you should slow your breathing, especially on the out breath, because that's what allows you to accumulate more CO2 until you can get back to baseline. And as you get back to baseline, that alarm signal will calm down and you'll go back to normal. But in the meantime, as long as you keep breathing, you're going to keep feeding into that circuitry that is sending off the alarm saying that you're suffocating, because it really doesn't know the difference. Yeah, I thought that was pretty interesting. It's especially interesting to me because it's relevant to me because I get panic attacks. That's a very vital piece of information, you know? Yeah, I think also my next video, I'm not sure who to do my next video about. I want so I have a few ideas for videos, but I want to do another video about maybe an ablation research case study or something. I have talked about Phineas Gage before, but not in years. So I was thinking I might redo a video about Phineas Gage. He's pretty important because he's how we understood that your frontal lobe is very important for your personality. The reason we know this is because he had a large portion of his prefrontal cortex damaged and just his whole frontal lobe damaged. I think by a railroad spike that, anyway, he became like an entirely different person for a little while. Although it seems like some plasticity occurred and he kind of went back to normal. Maybe not totally normal, but a little bit more back towards normal. I'm trying to think of other really important people. If anybody has a case study in mind that they'd like me to cover, I'd be happy to do it. There are other things that I think are very interesting, but I'm not sure if I should make videos about them because there is definitely like a dark side to neuroscience. I love neuroscience. I think that it's very important, it's vital, but there are definitely some like really wild things that people have done that are probably kind of shitty, I guess. Um, for instance, how we know the motor system is really important. It's not so bad. We know how motor and sensory function in the peripheral based on epilepsy patients and getting their permission to kind of poke around in their parietal lobe. And because we've been able to get their permission to poke around in their parietal lobe while doing surgery on them because, you know, they have epilepsy and they need a part of their brain removed anyway, um, you know, we know a lot about that. But before we had access to people, the first person to figure out where motor and sensory of the peripheral nervous system occurred was in the parietal lobe. They figured it out by experimenting on dogs, right? Um, which I find to be kind of, I don't know. Animal research is important. It absolutely is. There's a place for it. It's necessary. If we didn't do it, we wouldn't be able to work on humans. But it still just sucks sometimes to hear about that kind of stuff. But I had thought about making a video about that. I thought that might be interesting. I don't know. What would be some good, what would be some other ideas for videos? What do people want to see? What do you want to know about? Another really interesting topic that I like to talk about that I haven't quite made a video about, and I should, or maybe I did like a long time ago, like years ago, are patients that get nerve damage, but it isn't like total nerve damage. For instance, their brain receives input, but the kind of input that it's receiving is dark side of neuroscience long form video would be interesting. Okay, yeah, I'll keep that in mind. I might do that. Walter Walter Schweddy, is it Schweddy? Sorry if I said your name wrong. What do we need CO2 for? I know CO2 is important for certain processes. Hang on, let me look it up. Fun fact. So, fun fact. Actually, when we break down alcohol, the reason that we can break down alcohol is because we have enzymes that basically, through a process of just like you know the alcohol running through a series of enzymes, break the alcohol down into CO2 and water. So the effect that you get from alcohol is actually what you're getting from high levels of CO2 and water in your system. It says it's primarily crucial for uh, cerebral blood flow, widens blood vessels and vasodilation, right, to increase oxygen and nutrient supply for cognitive function. And having low levels constricts your blood vessels to reduce flow. So it looks like CO2 is mainly a supportive chemical that is used in regulation. We certainly don't need a lot of it because our cells sort of make it as a byproduct. Uh, Viome, sorry, Viome. I don't know how to say your name. Sorry about that. But formaldehyde. What would you like to know about formaldehyde? What about formaldehyde? Formaldehyde fixes stuff. It fixes tissue, makes everything unable to move. Oh, regarding alcohol, Are you talking about like how formaldehyde is broken down in the brain and in the body? Yeah. So, and actually, like some things, so we don't hear a lot about that, right? Like formaldehyde. Formaldehyde's very bad for you. um, Alcohol would be very bad for you had we not evolved with it to break it down. But there are things that, like, for instance, we were talking about glutamate earlier, right? Glutamate is super important, right? But it's also heavily restricted in its function because too much glutamate can actually do a lot of damage to you as well. Um, I'm actually not familiar with the process of how we break down formaldehyde. My only experience with formaldehyde is fixing brain tissue with it, and I know that that is a disturbing process. Oh, I wonder if you heard my cat. She saw her mom and got excited. Yeah, Viome, 8797. I will look more into formaldehyde and how we use it and break it down in the brain and in the body. I don't have my notebook though. Maybe Harm will write it down for me. That would be that would be interesting for me to do some research on. Yeah, the only experience I have with formaldehyde is just fixing tissue. I in one of my previous labs, basically in every lab I've worked in, I've used formaldehyde. But one of my previous labs, we would fix brain tissue and slice it, and then look at it under microscopes to see if things were there. You can see some of that work, I guess, on, I don't know, ResearchGate or something. I should probably link that somewhere. Yeah, I'll do a video on formaldehyde. Um, I want to do a video on a person. I want to do a case study, like an ablation study, but I'm not sure who to do it on. Who would be really interesting? I did one on SM, who is the gal who could not feel fear because of the damaged amygdala. I did one on HM, Henry Molaison. We can say his name because he's dead now. But he was important because he had epilepsy in his medial temporal lobes, and when they were removed, caused him to have an inability to remember anything. Limbic system retraining. Oh, sure. Yeah, that'd be a great video. Yeah, we can do some limbic system retraining. I don't know. I have a love-hate relationship with the limbic system because it is such a finicky system, and also we know quite a bit about it, but we still, I feel like, don't know enough about it. It feels very like, uh, well, because it's such a reactionary system, by nature, and it can be hard to pinpoint where certain things are happening because it has to do with so much of your life. But yeah, do limbic system retraining. Yeah. No, that'd be important. I should do this research anyway because I find myself stuck in fight or flight pretty often. Like I've talked about it. I'm pretty open about it. I have PTSD. It's like pretty shitty. In fact, one of my lives, I even, I don't know, I had like a little moment there where I had to regroup, which didn't go so bad actually. I was pretty good at it, but yeah, no, for sure. Limbic system retraining with PTSD and other fight or flight mechanisms. I probably should do a video on phobias. I've talked a lot about phobias on here, but I haven't really done any videos on them, like how they're created. That has a lot to do with that, right? The limbic system and the HPA axis, right? Your hypothalamus, your pituitary, and your adrenal glands. Um, Maybe I should do a video about that too, the HPA axis. Did I do one of those recently? I feel like I might have briefly touched on it. Yeah, that'd be good. That'd be good. What are some other things? I guess I could do some videos on drugs. Those might be kind of fun. Everybody likes drugs. I know for quite a few years, drugs were one of my favorite subjects to study. I just love psychoactive drugs in the brain. It's like wild, you know. For one thing, drugs wouldn't work if you didn't already have the mechanisms internally to do them, or to do whatever effect the drug is doing, right? So that's pretty cool. Like, how do you experience the euphoria from opiates if you don't already have a mechanism for euphoria, using your endogenous opioid system, which generally has to do with your endorphins, right? Things like that. It's pretty cool. The endocannabinoid system is one I like to talk about a lot. People talk about the effects of cannabis. A lot of people believe that cannabis is not dangerous, but it's actually much worse for you than probably most people realize, although most people who use cannabis don't usually seem to want to hear it. Yeah. What's cool about your endogenous cannabinoid system is that it is probably one of the most widespread systems throughout your brain and body. And in fact, it lines your heart muscles and your vascular tissue. So your blood vessels have these tiny little smooth muscles around them, and they are activated by your endogenous cannabinoid system. But that therein is the danger of it, right? Is because when you introduce exogenous cannabinoids by ingesting cannabis, then you're messing with your vascular tissue. And over time, that's pretty bad for your heart and blood vessels. I think that's about as far into that as I'll go. OCD versus generalized anxiety would be interesting. Okay, sure. Yeah. Could you maybe type some of these up in a note for me? If you can, you don't have to. Yeah, OCD versus generalized anxiety, or maybe even just all the types of anxieties, right? Because OCD is not necessarily a type of anxiety, but it is a disorder that is very comorbid with anxieties and is thought to be derived from anxiety. OCD being specifically derived from the inability or feeling like you have an inability to control your life, and so you start obsessively trying to control aspects of your life. Oh, really? Cool. Okay, good. Good to know. I didn't know that YouTube saves my comments. Yeah, I'll be able to come back and watch this again. Yeah. I think it would be good to do a long form video about anxiety disorders and maybe tack OCD onto that. That's my cat. Let's see. I think I could include phobias into that video. I am getting ready to do long form content too. I just really want a whiteboard first, but I guess I don't need one. I am saving up for one. I did get monetized on TikTok, by the way. It's not much, but it's honest work. So as soon as I have money to do something with that, I might buy a whiteboard to pay to have some editing done to some of my videos. Donations are always welcome too, obviously. I do need better recording equipment. We've covered that. If anybody has anything, I'd appreciate it. Let's see. Oh, some other news is TikTok's still growing. That's great. TikTok's usually pretty steady, but YouTube has been steadily growing as well. And we surpassed 3,000 followers on YouTube since the last time I've been live. And not only surpassed 3,000 followers, we're actually almost at 4,000 followers on YouTube now. And Instagram is doing really well too. We're actually almost at 10K. We're like this close to 10K on Instagram. So just letting you all know that you have lots of siblings out there that are also interested in the brain. And it's just really cool to see this community growing. I really appreciate that. People share my love for neuroanatomy and neuroscience and just how the brain and body function. It's kind of a humbling and honoring thing to just kind of have this community. Thank you. Thank you. Yeah. Anyway, I just want to thank you all and congratulate you as well for your awesome community, that you're building, that we're building together. Um, yeah, that being said, man, I cannot wait to start making long form content on YouTube. I think that that will just be the bee's knees. And I can put it up on YouTube too, I guess, or I mean on TikTok as well. I think TikTok allows longer form videos now up to 10 minutes. That's pretty cool. I don't think that I might have one 10-minute video on TikTok from like a couple of years ago. I think that's about it. Yeah. I definitely want to do a series. Just like I know a lot of people love neuroscience. They want to know about neuroscience. They want to know more about the brain and behavior and things like that. But they're like, how do I get started? Where do I start? And so I do want to start doing lectures from beginning. Like, where do you start? Where is the absolute beginning, right? Lecture. And moving forward to as complex as we want to get. And I will probably be doing that soon. I might have my very first long form video on that out soon. I'll try to make it like long, but like, I don't know what's a good amount of time, maybe like 15 minutes, 10, 15 minutes. I'd like to know what we've learned about the brain via cats. I think you've mentioned in the past, cats have taught us a lot about our own brains. 15 to 30 minutes is great. Okay. Yeah, actually, cats have taught us a lot. Most of what we know about the visual system we got from cats. We know that your primary visual area in your occipital lobe, usually termed V1, right? Your primary visual cortex is responsible for edge detection. And so, we used to think for a long time, oh, you can see objects like a circle. And you'd go, oh, there's a part of the brain that says that's a circle. And it really doesn't work that way. Actually, your brain can't really see circles so much as it can see lines. And it can kind of see lines, but even better, it can see lines moving. And it pays attention to a line moving, but it also pays attention to what angle the line is moving at. And you can have a series of really complicated lines making round shapes or corners or whatever. And so that's when I say edge detection, I'm referring to this process of detecting the edge of an object using these lines, which can get quite complicated. And, that will be part of my lecture series too, when I get to talking about the visual system, because, learning how simple and complex cells work together to form shapes in the brain is pretty amazing. But even then, that's just identifying a line moving, right? How do we take a line that's moving and turn that into a color? Or how do we turn that into a distance, right? How do we turn that into, oh, that's not just a series of lines, that's actually my aunt, like we need much higher order processing for that, right? To know something is a baseball and to see and to calculate how fast it's moving, you need your parietal lobe and your temporal lobe for that as well, right? It's not just your visual system. You need much higher order thinking for those things. That stuff's pretty interesting. I don't know. Oh, okay. You know what? I should do a video on that woman. I don't remember her name. I think she might still be alive, so that might be why I don't know her name. I might know her initials. I don't remember her initials. But there is a woman who had received damage to her parietal lobe. Really quickly, your parietal lobe is, so like if this is the front of your brain, right? Your brain's oriented this way. Your parietal lobe is at the top here. And you have what are called the what and where pathways in vision. And so when you're talking about vision, the first thing that happens is the visual information you receive from your eyes goes to your V1 in your occipital lobe. Your occipital lobe is at the back of the head, back here. And then that information can either go up to your parietal lobe, that's the where pathway, or it can go through to your temporal lobes down here. That's the what pathway. And so we know that people who have damage damage to, there's one person, I can't remember who they are. I literally remember almost zero facts about them. The thing that I remember is that they had their temporal lobe damaged in such a way that the part of their brain that interprets color, which happens to be in your temporal lobe, and it's that pathway going, it's the what pathway going from your occipital lobe to your temporal lobe that interprets color. And so this person was unable to interpret colors that they saw because they had this pathway damaged. But there's another woman who is really interesting. I just haven't thought about her in years, but like, I think I've briefly mentioned her during another live a couple weeks back. But you know, she had what's called the MT. It's a part of your motor region, which is up in the parietal lobe. This is the what path or the where pathway, and usually determine where other objects are in relation to us ourselves. And she had received damage to that part of her brain and was unable to see. She was unable to see continuous vision, right? Like motion. She wasn't able to detect motion. And so she saw the world as a series of snapshots, right? It would be, and it made like really simple things become very impossible for her. You know, like we take for granted walking across the street, but the reason you're able to walk across the street is because you can see a car coming and you can determine what speed it's coming toward you. But she had no ability to do that, right? Because she lost that part of her brain that interprets fluid motion. And so she experienced snapshots. She would look down the street and she would see a car, and then in literally like a blink, the car would already be a lot closer, and there was no in between, and it would just be snap, 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 you know. So yeah, she couldn't cross the street without assistance. And it made like other things like, right, how would you play sports? You couldn't play sports doing that either, right? Yeah, anyway, she's really important. That ablation study is really important for neuroscience because that's how we understood that part of the brain region was really important for that kind of visual processing. And also that's how we understood that visual processing is not just done in the occipital lobe, right? There's an important thing about the brain is that, and here's another thing about ablation, right? Ablation being like to receive a cut in the brain, right? These studies are very important. So the thing is, we always wanted to map the brain. Every textbook maps the brain, right? Any textbook you look at maps the brain. My cat's checking me out. And so we say, oh, the frontal lobe is for your personality and your higher order thinking, and for decision making, impulse control, planning, timing, things like that. Crossing the street? Tell me more. I want to know more about that. And we say, okay, your temporal lobes are responsible for your auditory processing. Your occipital lobe is important for vision. Your parietal lobe is important for motor and sensory, and etc. Right? And it can be easy to like fall into this wanting to map the brain, but the truth is that your brain is so active that a lot of these areas overlap with each other, and they can get quite muddy. And especially when you lose a sense, then other parts of your brain that should be, in theory, doing a different sense will start to be incorporated for other senses that you do have. So here's what we know based on ablation studies, and we actually know this from animal research, is that, you know, somebody goes, I want to know if auditory processing happens in the auditory cortex, in the temporal lobes, the auditory cortex and the temporal lobes, which this is your temporal lobe, right? And the auditory cortex is like in this crack here. And so one way you do that is you go into a mouse's brain and you cut it. And then you say, hey, can the mouse hear? Can it understand what it's hearing? Right. And what will happen is that mouse will suck at hearing really bad. And you go, oh, eureka. This is where sound is processed in the brain because this mouse cannot hear anymore, or it can't interpret what it's hearing. And you go, oh man, Well, I guess that's important to know. But then you test the mouse like a week later and the mouse seems fine. And it's like, well, how did that happen? You go look at the brain, it's still ablated. So why is the mouse able to still do the thing? Well, initially it couldn't because you severed the connections that were originally there, but because of neuroplasticity, it's able to reestablish connections. It turns out losing functionality of your brain usually has less to do with where the cut is and more to do with how much of the brain is cut, which is a really interesting concept. And I might have to do a video on that as well. Yeah. Really quick, Viome 8797. I want to know more about what you're saying. They say, oh my God, seems like that happened to me crossing the street. In about 10 minutes, crossed the street twice and was nearly run over by a car. Just appeared in front of me. That's interesting. I want to know what's going on with that. Do you normally have, and please feel free not to share any of your medical history with me if you don't want to. You're not obligated by any means. I am interested to know, do you have visual processing issues that you know of, that you're aware of? Because sometimes that can be an attentional issue as well, right? Oh, thanks for the gift, Pekka. Yeah, attentional awareness can also be an issue. Oftentimes, so here's something that I've talked about. I should definitely do a video about this as well. But something that I usually talk about when we go live is how the me, the you, the thing that wakes up and is here right now and is with me and thinking about the things that I'm saying, you're a very small part of your brain and not a particularly important part either. Like kind of important, but like really only important in certain contexts, but you take credit for a lot of the things that the rest of your brain is doing for you. Showering takes too long. I'm sorry. Well, hopefully it was a good shower. Yeah, I'm glad you're back. Just dizzy and brain foggy. Uh-oh. That's not good. Dizzy and brain foggy. Viome, that I don't know. I understand that people get dizzy and brain foggy sometimes. Is that like a normal occurrence for you? Do you were you just not getting enough sleep, or what do you think was going on there? But yeah, so the thing that wakes up in the morning and goes, I'm awake and I'm autonomous and I'm responsible for all my decisions. That thing is actually a very small part of my brain. The rest of my brain has been doing a lot of work, some of which it did while I was sleeping. But, I'm happy to get up and take credit for it, And here's the thing is like, because I'm not necessary for my brain to do a lot of things, my brain will do a lot of things without me, right? And so we kind of say that this is like a lack of consciousness in a way. And this is when people are generally sort of daydreaming. And this is also why people can do things like go from, one place to another place and not remember the journey at all. It's usually because you've been there and you've done that journey 1,000 times. And so it's no longer novel to you. And since nothing is new, every little obstacle by heart. You, the CEO of the brain, doesn't really need to wake up for it, right? So you unconsciously just go through life and you don't even realize anything has happened. And I think that's kind of a necessary part of existence too, because although, we should really think about this, especially in terms of like mind control. I know people love talking about mind control. So like actual mind control would be really difficult, by which I mean controlling someone else's thoughts would be really difficult. But putting someone can be restful to an extent. Sure, yeah, it is exactly. That's exactly the point. So sure, like controlling someone else's mind, like their very thoughts and actions, not very possible. That's actually really difficult. But it is possible to put somebody into a trance. And the way you do that is through things like social media and television. Television's the big one. That might even be why television was invented. But the thing is that it puts you into a theta brainwave state, which is very similar to dreaming. And that dreaming state is where you are less conscious, right? Your CEO doesn't really need to be awake for that, right? And like Harmony said, it can be restful to an extent. Well, that's kind of the point, right? Is because it's all about energy conservation. And if you think about evolution, it's all about energy conservation. In your brain, when you're not thinking too terribly difficult, if you're not thinking too terribly hard, it sucks up a lot of energy. Probably about 5% of your daily caloric intake, right? Your brain uses a lot of energy. It uses a lot of your energy. So how do we survive? How do we survive long periods of time where I'm not sure when I'm going to get to eat? And I'm thinking in terms of my ancestors here, right? I don't know when my next meal is going to be. Well, one of the ways that I can survive with my OCD, I bet I'm cooking along at 50%. Yeah, probably more than that. So the thing is one of the ways that we survive evolutionarily is to not allocate resources when it's not necessary to allocate them, right? Conserve. And one way that you can conserve is by limiting your brain power, right? If I don't need to use my brain, I'm not gonna. And so it's very natural for people to fall into that very easily. It's just natural to not want to think too hard because that's part of your evolution. I'm going to encourage you to fight that part of your evolution, but because I find that particularly rewarding. But the other reason why is because there are people who take advantage of that. They know how to put you under a trance and tell you stuff, so you got to be careful. And like what I'm saying, I know it sounds ridiculous, but it's true. And this has been a thing for decades and decades and decades now. If you really want to look into it, look into what's that guy's name? Is it John Watson? I always get him confused with the DNA guy. I think the DNA guy is James Watson. Or maybe he's John Watson. Which one's which? Yeah, John Watson. John B. Watson. American psychologist who popularized the scientific theory of behaviorism. He was also known for the Little Albert experiments, which are somewhat contested. If true, he's a huge piece of shit. But one of the things about him, though, is that he was actually kicked out of the field of psychology. He was removed from psychology. And it wasn't because his research was bad research. It was bad. But not like bad, like, oh, the data is bad, the idea is bad. It was bad because it was unethical, and that's why he got kicked out of psychology. What he did after that is immediately go into advertising, and he had a very lucrative career in advertising. And it's because he figured out that it's really easy to sell people stuff by playing on their emotions. It's really easy to manipulate people to get them to buy stuff, right? And he was really famous for his ads. In fact, you've probably seen a few. These really old-timey ads from like the 50s that say just the stupidest stuff like, who could love a woman with smoke-stained teeth? Try Colgate. You don't love your baby unless you try Johnson & Johnson baby powder. Those are literal ads slogans that he developed. I'm not kidding. You can look those posters up. Those posters were created by him. He had a very lucrative career because he was able to make people feel terrible about themselves until they bought his products, right? And not his products, but the products for the companies that he worked for. And of course, our government knows this. Our government uses this and far beyond, right? That's good advertising, though. Just guilt trip them. Sure, Sadie. Yeah. I mean, you're not wrong. It's if it gets them to buy your product, that's advertising. Nagging people into buying stuff. Yes. It was very effective. It was extremely effective, right? And he wasn't the only one to do that. He wasn't even the first one to do that, right? Like World War II was all about that, right? Ladies better shave their legs and start buying razors. That was part of that. Like my wife's looking at me like she's got something to say.
I do, but it's too much.
Is it too much? Do you want to join me?
It's related to nylon tights.
Do you want to come share?
No.
I have another
No,
microphone.
I'm exhausted.
She's exhausted. She doesn't want to share about nylon tights. Everybody guilt trip Harm into telling us about the nylon tights.
No.
Eat carrots for better eyesight. Yeah, for sure. Try meth. Maybe once. I don't know. Don't do that, by the way. Yeah. And I mean, there's a really good book on this too. It's called Subliminal. I'm looking up the author. It's Subliminal: How Your Unconscious Mind Rules Your Behavior by Leonard Mlodinow. That's a very odd last name. Because they had to have the lights off in the cities so they couldn't be bombed or something. Could be wrong. Interesting. I have not heard about that. So eat carrots to see in the dark. Okay, that's interesting. That's really weird. Thanks for the tidbit, Sadie. I'll look into that. I don't doubt it. But yeah, exactly. Like, and then Harm has a story about nylons that they won't share because they don't like us. So
I'm in a pen crash right now. If you must know.
I'm sorry. Yeah. Let me think. Hang on. Let me drink some water. Eat carrots. Yeah. It's so funny, because we really haven't changed, right, Sadie? We still have the same thing going on. The carrots thing is a true falsehood that they spread. Yeah. And we still have that going on today, right? That like literally nothing has changed. And that was done in the 1930s, and literally nothing has changed. I just did a video about how people are all about NAD supplements now. And it's like, okay, but you can't really eat NAD. You take that in a supplement, your gut will just digest it. You might get a little bit, maybe some of it will make it to your brain eventually. Not really NAD, but the precursors to NAD that you've digested it into. Most of them are going to break down and become nothing. I mean, they're not going to be nothing. They're going to get used by your body somehow, but they're not the equivalent of NAD. Some of it might become a precursor that gets to your brain and eventually becomes NAD, because that's how your brain naturally makes NAD, right? But like everybody is just all about NAD supplements now because the NAD is necessary. NAD is vital, right? It's vital for memory function. It's vital for neuronal cell health and stuff like that. But you can't really take a supplement to make that better. To make it better, you have to live healthy. That's it. And that's basic biology, and it works every time. But Sadie, for the same reason, you better eat your carrots so that your eyesight gets better. Mihaela, hi. And also thank you. It's good to see you. But yeah, people are still just buying the BS. It makes me think of this one guy who he told me something sometime, and it stuck with me. I think it'll stick with me the rest of my life. He said, I have half a brain that sells bullshit and the other half likes to buy it. And sometimes like that makes me think about people a lot, right? Because we buy a lot of bullshit, if we'll let people sell it to us. Especially in times like these where it's just times of everything's just so hard now, there's just too many hard things happening in the world. There's atrocious things happening all over the place. And like even in the US right now is awful. And it's tough. It's tough. especially with like COVID as an ongoing pandemic and things like that, people stop trusting things like the CDC, and for good reason, right? Um, and you don't know who to trust. And now people are starting to like kind of, I don't know, it's so weird. People debate germ theory. They More people are becoming flat earthers. Um, we're kind of like headed back to the dark ages, you know, and that is a very predictable trend that we kind of knew sort of thing happened, and it did happen, and now it's happening. Um, it's strange, but it makes people easy to control when you know how they're going to behave. You know, you started doing witchcraft. Good for you. Good for you. I hope that you know what. I hope it works out for you. Um, Here's something a lot of people don't think about: is that's science. You know, is it good science? I don't know. That depends on the person, right? If you're doing good science, you're trying to be unbiased, and you're performing experiments, and then you're recording your results. And I don't think witchcraft gets taken seriously, so I don't think it'll ever be seen as like a science. But that doesn't mean that the science of spirituality doesn't exist, you know. And I think that people should try more stuff out, and they should record what happens. That's science. It isn't science to be like, that's bullshit, don't even look at it. You know, that's the opposite of science. That's what Republicans do. Borderline, so I guess we'll find out what happens. All right, yeah, let me know. Record your results and send them to me. You don't have to. Don't feel obligated, but I would like to know if anything fun happens. Also, it's just fun to it's fun to just relax a little bit and just do something that feels good. You know, who knows? Play video games, whatever. Have your experience that your ritual that you need for you. Whether your ritual is playing Call of Duty or if it's sitting in front of some candles and reading a book or whatever, you know, drinking some tea or whatever. It's good for you. Suspension of disbelief for even a brief time feels good. Yeah, exactly. Sure. I mean, yeah, sometimes it's good to just shut the thinker off, you know. Here's another thing. There's a quote that's often attributed to Herbert Spencer, but I don't think Herbert Spencer was the one who coined this. Coin's not the right term. Hang on one sec. I'm gonna look up this quote. It's a good one. I'm getting a little bit tired, so I might have to hop off here soon, but I did want to share this quote first, and maybe it'll be a good way to just a good thing to leave the live with. Let me just see if I. Yeah, so this definitely seems to be attributed to Herbert Spencer a lot. I'm not sure that it is actually him, but I'm gonna, just because all these other sources seem to say that it's Herbert Spencer, I'm gonna go ahead and go with maybe it was Herbert Spencer. But I'm pretty sure I did find one instance where this was said before him. But anyway, he said, "There is a principle which is a bar against all information, which is proof against all arguments, and which cannot fail to keep a man in everlasting ignorance." I'm going to say that again. And this isn't the entire quote. I'll say the rest of the quote after this, but I want to repeat this. There is a principle which is a bar against all information, which is proof against all arguments, and which cannot fail to keep a man in everlasting ignorance. And that principle is contempt prior to investigation. That principle is contempt prior to investigation. So he said, it doesn't matter if the person feels contempt before they've even taken the time to try to get to know the thing, they will stay ignorant, and there is nothing that you can do to change it. 145. What, like AM? Where are you? Yeah. A bar against all information. And there is no argument against it. If a person doesn't want to know, they're not going to know. You cannot teach a man anything. You can only convince him to teach himself, Yep.
1:45 a.m. has to be the UK.
You in the UK? Where you at? You don't have to disclose that, I guess. That's fine. But also go to bed. What the heck? It's Thursday. London, really? What's that like? I want to move to London. I actually, I want to find a job in London. I'm looking for work right now. I've been applying to Germany 245. What's up, Walter? Oh, so it is Schwede. Or is that how you say that? Did I say it wrong? I'm sorry if I butchered your name. I did think that looked German. Is it Schwede? I don't know how to say that. I'm sorry. I'm sorry, Walter. Or is it Walter? I don't know. I know W's and V's are mixed. That's about the extent of my knowledge. I actually did study German in college. We had to learn another language. Usually you have to study another language in the US during your undergrad, and German was the one that I studied. Yeah, I did 2 years, and I don't remember anything about it. I wish I did. I actually really like German a lot. It sounds really cool. Yeah. Yeah, and I'm definitely interested in finding a job in Germany too, for sure. That'd be pretty cool. Just silly little Americans doing our best. Just silly little US citizens doing our best. I like that too, how we always refer to ourselves as American as though there aren't other types of Americans.
Yeah, but U.S. citizens, let's just say.
Guten Abend. Yes, exactly, Cynthia. Good evening. Is that what it is? Evening? Yeah. Gute Nacht is night, right? I think that's right. Yeah. Cynthia, how are you? Yeah, I'm looking for work right now. I am working as a tutor here and there, but I need to come up with enough money to just get us out of here. I am not happy with the US right now. I was looking at some Thermo Fisher jobs in the UK. I was thinking about maybe like Spain or something. I think that'd be cool. Grass is greener, sure. But also, I don't know if you've seen the news, but it's pretty rough here right now. Cologne? All right. I'll look. I'll check it out.
It's France, right?
Germany.
Oh, it is?
Yeah. Köln Altstadt Nord. Okay. Yeah, I will look into it. Thank you for the suggestion, Walter. Yeah. When you're going night night? Okay. Thank you for that, Cynthia. I appreciate the confirmation there. Yeah. What do I remember? I remember Schnee is snow, which is one of my favorite words. I just like that word a lot.
Somebody asked a question about resistance.
Oh. I did not see a question. Oh, is there an explanation for deja vu? Okay, Cynthia, yeah. Let me read your other comment real quick. Germany is also not so good. Salaries are very low compared to the US, and taxes are pretty high. I hear that. A lot of people have a problem with the salaries being low compared to the US, but I got to tell you, I had a really high paying salary in New Haven, and I could not afford to live because of how expensive everything was. So, I know that it seems like salaries are higher here because they are, but also the cost of living here is crazy bananas. It is so high that it really does become unlivable. It's ridiculous. You still even live in Hamburg. Okay. Where do you live now, Cynthia? If you don't mind sharing. And I'll answer your deja vu question really quick while we're at it. I like this question. It's a fun topic. So deja vu used to have I'm going to tell you the old theory and I'm going to tell you the new theory. Okay. The old theory of deja vu was that it was just based on experience, right? Let's say that you one day when you were a kid, you went into a green room and it was a very particular green and you never really saw it again. And then another day you ate pizza at a Chuck E. Cheese or something. If you don't know what Chuck E. Cheese is, they're probably pretty obsolete now. But like, it's basically just a place where you go.
Children's casino.
It's a children's casino and rat pizza. It's a place where you go where a giant mouse hands you pizza and a bag of tokens, and you play arcade games, and it smells like cigarettes.
Magical.
It's a magical place with animatronics that sing and break down. Anyway, it doesn't matter. The point is, let's say then later, that happens, whatever, time passes by, way later, you end up in a room with an animatronic, and that room is that same particular green. And you have experience with both of these things. You might conflate the two as the same experience. And so you think, oh, I've definitely been here before, right? And it gives you this eerie feeling, man, I've definitely done this before, even though I know for a fact that I haven't. That was the old thinking. That's how people used to think deja vu happened. But now we have a different theory, and it has to do with Baddeley's model of working memory. So now that we've come up with a model for working memory, that seems pretty good. It definitely answers a lot of questions. Basically what happens is you have sensory memory, you have short-term memory, and you have long-term memory. And your working memory is pulling from your sensory memory and your long-term memory to hang on to things in your short-term memory and work with them, right? But the problem is sometimes you're in an event where your brain searches your long-term memory for something that doesn't exist. You have no experience with it. And at the same time, it's such a novel event that your brain is feeding it into your long-term storage at that same time. So we now think that deja vu might be a phenomenon where you are feeding the information that you're experiencing right now into your long-term memory, and then your working memory is pulling it back out to try to relate it to your current experience, which doesn't make a lot of sense. It's like, how, because it's not a long-term memory, it's literally happening right now, right? But you perceive it as an old memory because, hi Chibi, how are you? It's good to see you. It's easy to perceive it as a long-term or an old memory because typically that's how long-term memories work. I remember this from a long time ago, right? Yeah. So that's the current model of deja vu is you're storing the information and then pulling it right back, and it gives you the overwhelming experience like you've had this information for a really long time, even though you've just recorded it for the first time. I'm good. You know what? It's been pretty rough, honestly, but I'm doing the best I can with what I got. Harm's doing the best that she can with what she has. We're doing our best. But it's good to see you. I hope you're doing well. How does EMDR work? I still don't know. I know that bilateral stimulation is so there's something about bilateral stimulation, which if you don't know what that is, it's like moving opposite sides of your body, or contralateral, you might say, sides of your body in sequence, and they don't necessarily have to be at the same time, and they don't have to be aligned, right? Or rather the timing can be offset, right? So like, I could be tapping my fingers at the same time, or I could tap one and then the other, and then this one, and 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 this one. You get the idea. This might be a little tough for somebody like Harmony. She has to use her toes. But the point is, when you're rhythmically stimulating both sides of your body and thereby both sides of your brain, you are syncing your brain up and getting it into like a nice stable state. So I think part of the theory behind EMDR is, when you're experiencing a lot of upset cognitively, uh, the waves of your brain are also in sort of an erratic sort of. I don't know how to say that. It's like the activity's all over the place, right? When you are alert, different parts of your brain are oscillating at different frequencies. And sometimes your hemispheres even can split up their frequencies. And that's not very good. That's bad, right? And we can see this a lot with like phobias. We see this a lot with PTSD and panic disorders. And so EMDR, my understanding is that one aspect of EMDR is that it helps to sync up your hemispheres and regulate your thought processes while you are in a state of thinking about something that would traditionally trigger you, right? So normally you think about this thing you don't like thinking about, it triggers you, your brain becomes erratic, you're all over the place, and it's very discomforting. That's the nature of the disorder. It causes disorder in your life, right? But here we're going to put you through that, but we're going to try to control it by controlling your body. And then by controlling your body, we're controlling your brain. And by rhythmically resetting your brain, you can have these thoughts in a more controlled manner. And you stop pairing these thoughts with anxiety and pairing them with crisis, and you start logically interpreting them, I suppose, is the idea. That's my best understanding of it. I hope that's a good enough answer. There's more I could know. Eyes as well. Resist oppression. What do you mean by eyes as well? You mean moving the eyes? In which case, absolutely. Yeah. I definitely did see that. A lot of like up and down and back and forth movements. Yep. Hang on one second. Okay. Yeah, good. Okay. I am going to have to take off. We got to wrap up. I got chores, got groceries I got to go pick up. But I just want to thank everybody. Thank you, Chibi. Thanks for the question. I want to take a second really quick because I have enough people here. Congratulations to YouTube. We're almost at 4K. That's amazing. I literally have no idea how we've been growing so fast, but I really appreciate it. Thank you for being part of my community. Thank you for all the questions. I hope I was able to answer them, in a satisfactory manner. If I'm not, find a way to reach out to me and tell me I suck, and I'll do better in the future. I'm always open to feedback. Everybody knows that. Came to work for the U.S. Oh, okay, cool. Yeah. Well, I'm glad you're here. I hope you like it. Is it Elmies? Thank you so much. I'm glad that you like my content, and thanks for being part of our community. Work in my field. Netherlands. Okay. Thanks, Cynthia. Yeah, thanks for the recommendation. I'll look into it. That being said, we've also made a lot of progress on TikTok. I am monetized on TikTok now, which is pretty awesome. It's not a lot of money, but whatever money I do get through here, I will put towards my videos. I am hoping to do long form videos here soon. Yeah, I can't express my gratitude enough to all of you. Thanks for being part of my community, our community, this thing that we're building together. And yeah, feedback's welcome. With that, I guess I'm out of here. Thanks, folks.